Hello guys, today we're going to be doing inferential statistics and I've made a document full of notes. This basically sums up the entire chapter of inferential statistics, which is by far the most important chapter that is in the further stats variant of the further math 9231 CIE, as these questions usually come in a total of 15 marks in the 50 marker paper. So yes, it is the most important chapter and therefore it is essential that everyone must know how to use these formulas to solve the problems. So let's begin. So over here I've listed 4 different types of questions that they ask, the most commonly ones. Now I'm not saying that these are the only questions, there are different types, but the most common ones that are asked are type 1, 2, 3, 4 as shown over here. Alright, so let's tackle each of these in the way they should be. So over here we have here for the type 1, test the claim. So this is one of the most popular questions, and at least one kind of question will be here in the test, and this is the first type, and that's a single sample test. So the values they give are this mu, which is the stated mean in the question, nx, which means that that's the number of terms that are there in the sample, sum x, meaning every x is summed up. So if these are my samples, sum x would be this plus this plus this until you get here, and sum x squared would mean all my samples went squared and summed up. So I squared 48.8, then we square 48.2, and we add them all up until 48.4 squared. So these are the kind of values that you would be needing. Okay, these are the startup values. Okay, let's move on. So in the question they usually ask you to test a claim whether this mean is greater than, lesser than, or equal to a certain value. That certain value is your mu as stated. So the first step I'd usually do is state the hypotheses, where H null, which is your null hypothesis, always should state that the mean is the value stated in the question, whereas your H1, which is your alternative hypothesis, must always state what the claim is not stating, which the claim is stating actually. So if the claim states that test whether the mean is greater than 8.2, for example, that means that your H1 will mean this right here. It could be mu lesser than k, or sometimes they may say test whether the claim is equal to 8.2. H null will be mean is 8.2, H1 will be mean is not 8.2. So this basically combats the first null hypothesis. Moving on, step 2, calculate S2x. This is what we call the unbiased estimator of x. So to calculate S2 of x, we need to use the formula over here as shown, and there is another formula for this. I'll come to that when solving the questions, but basically when you plug in this exact formula, you're going to get S2 of x every single time. So 1 divided by the number of terms minus 1, which is basically the degrees of freedom, and we whole multiply that with your sum x squared minus sum x whole squared. There is a difference between sum x squared and sum x whole squared. Okay, so sum x squared, all your values squared and summed up. Sum x whole squared is all your values summed and you square the whole value there, and then we whole divide that with the number of terms you have, which is nx. That's your S2 of x. Now step 3, actually step 3 can be carried out in any state except the fact that it should come before step 4, which is quite important actually. So calculate x dash, that's the overbar, so that's basically going to state your mean of the sample. So this is the most basic stat operation that you can do. To find the average in a number of samples, you're going to calculate the total and divide it with the number of terms, which is basically sum x divided by nx, which is number of terms. So we need this and this. Okay, so these are 2 values that need to be calculated. Everything else can just be plugged into the formula. Now step 4, calculate the test statistic. So x dash minus mu divided by root of S2x divided by nx. So there's not much explaining into this question. It's just that you need to be plugging this formula inside. For a single sample test, the denominator is this always. This is quite common to remember, but this can be a little tricky. Finally, we need to calculate the critical value. So once we've done with the test statistic, you must know that to test whether the claim is true or false, it needs to be compared with the critical value. Now, critical value can lie in the normal distribution range or the t-distribution range. What I mean is this. So the critical value would be lying from here to here, can be any one of these. This p value just corresponds to one of the critical values here, right? So once you calculate your p, your critical value can be here or it can be anywhere over here where you've calculated your p. So the only thing that's differentiating them is that we have the degrees of freedom over here. So if the degrees of freedom is calculatable, that means that you're going to have to refer to the critical values of the t-distribution. For example, we have 10 samples. Your degree of freedom will be 10 minus 1, which is 9. 9 is there. So that means that your whatever p value you have will correspond to the row 9. However, if we had, for example, 76 samples, the degree of freedom is 75. We don't have 75 anywhere. So now we go over here. So that's just basically how you use the critical value tables. Very simple, not very difficult. Okay, so just as stated in the document, we first use the level of significance. Okay, this is to calculate the p-value. So if h1 states that mu is not equals to k, means that it's a two-tailed test, meaning that mu can be greater than or lesser than k. So we don't know that. So that's what we call a two-tailed test. If mu was greater than k, then we look at mu values that are only greater than k. In this case, it can be greater or lesser than. So we convert the level of significance to a decimal, and then we divide the significance level by 2 to get the value alpha. Then we perform 1 minus alpha to get the value p. If mu is greater than or lesser than k, it's a single tail test, and we directly do 1 minus alpha by p equals p. Right, so this is basically what explains the entire thing. Okay, so if we have, like, for example, a 5% significance level test and it's a two-tailed test, we divide the significance level by 2. Okay, so let's say that was 5%. We convert it to decimal as stated. That's the first step. Next, it says that we need to divide it by 2. This is your value alpha, and then you have to plug in 1 minus alpha. So 1 minus alpha gives you 0.975. Now let's say that we have 10 samples. So your degree of freedom will be nx minus 1, which is just 9. So at this p-value 0.975, you look at degrees of freedom 9 and 0.975, you will see 2.262 is the value that overlaps between the two. This is your critical value. This is how you use it. Okay, so yes, that's quite important. And since we've used the values over here in the t-distribution, we call the critical value as a t-value. If we used any value over here, we call it a z-value, but they don't really grade you based on that, so it's not too important. And the last step, which is the last step of every single test, step 6, comparison and conclusion. Okay, so the t is considered test statistic. Do note that if your critical value you calculate and you get a value from the t-distribution, we call our test statistic t. Okay, and if we get it from z, we call the test statistic z. So they don't mark much on that, but I have seen marking schemes and they usually do use variables in it. So it's important that you use the degrees of freedom to get an idea of what your test statistics variable will be. But it's just a side note. Alright, so if the test statistic is greater than the critical value, we obviously reject H null. Okay, and this is there for every test except for the non-parametric tests. Right? Okay, so if t is greater than the critical value, we reject H null, and always, this is the structure that you need to form, and state that there is sufficient evidence to support the alternative hypothesis. Okay, so this is a structure that you need to always state. Sufficient evidence to support. And this alternative hypothesis, we don't write alternative hypothesis. Instead, we just state whatever H1 was stating. So we can say, in this case, state that there is sufficient evidence to support that the mean is greater than k, or whatever. It's just like that. And if t is lesser than the critical value, we accept H null and state that there is insufficient evidence to support the alternative hypothesis. Once again, we just insert whatever our alternative hypothesis was stating. So let's tackle a question based off this. Right, so over here we have a single sample test. There we are test at 10% significance level, the null hypothesis and the alternative hypothesis. Okay, so they've already stated out a null and alternative hypothesis. However, just for good practice, I'd like to state them and write them down. So H null, right? This is what you're gonna write. H null. And what do we write over here? We're gonna write mu is equal to 8.2. Mu equals to 8.22. 8.22. Okay, and your alternative hypothesis is already stated as shown that the mu is lesser than 8.22. Okay, this is really important. Okay, this time it won't be graded since they've already stated our null and our alternative hypothesis, but there are questions that don't state this, so it's important that you crack this first step. Right, so the second step they say is to calculate S2 of x. So we can just plug in our values directly, right? No, we can't. We don't have the given values here. We have mu x, we have number of terms of x, we don't have these two, however, so we cannot calculate S2 of x directly. So we need to calculate the sum x and sum x squared individually right now. So I'm going to write this in red, right? So sum x, and this, they've given us some data values here. Alright, so we need to use these data values to get our sum x and sum x squared. So let's first get sum x. Sum x will be all the terms added up together, 7.78. Right, so we're just gonna double check if all our values are right. 8.34, 7.95, 8.27, 8.04, 7.92, 7.78, and 8.26, and this gives us a value of 56.56. Okay, so let's put that here. Right, next value that we need to calculate is sum x squared. So just if you've had any doubts in what I've explained of sum x squared, I'll clear it out right now. So we're gonna add up each term, but before that we square them up. So 8.26 squared plus 7.78 squared plus 7.92 squared. Like this we go on for each and every one of these terms. So we can do this. It's quite a tedious process, but they don't usually give you data values to just solve. They usually give you our sum x and sum y and all that. And yes, let's just cross check. It's important that we cross check that our values are right. If they aren't, our entire test could go wrong. I mean, the slightest decimal variance could affect our calculations. And we have here a decimal value, which is good. 457.275. Now we have all the values that we need to perform S2 of x calculation. Okay, so I'm going to write here S2 of x, and this is equal to 1 divided by, so the formula states 1 divided by nx minus 1. Nx, as I said, is the number of terms. There are 7 observations, meaning that there are 7 terms to use. So nx minus 1 means 7 minus 1, which is just 6. Okay, and next part of the formula states that you need to use sum x squared minus sum x whole squared divided by number of terms. This part is important as this is basically the defining part of it. So we have to write sum x squared minus that with 56.56 whole squared. We have to whole square this value and divide that with the number of terms, which is 7. Okay, so this is our S2 of x value. So I'm going to calculate this right now. So we have 1 divided by 7 minus 1 is 6. We don't need to plug that right in. So we have 457. Let's just define this point a bit. Yeah, 2.75. So this is our sum x squared. As for the other one, we have 56.56 whole squared divided by 7. And this is our S2 of x, which is 0.0503. So which is equal to 0.0503. it's recurring, but yeah, we can just put that. And however, we use this value, the fractional value, in our calculations because we want it exactly correct. So we need to use the value given in the calculator. 1351 divided by 30,000. Okay, so this is just basically a fractional value. Okay, moving on. You calculated S2 of x. Now let's calculate mean of x. Mean of x, very simple to calculate. We can just write it like this: x dash equals to, so the sum of terms is 56.56, and we divide that with this number of observations here, and this should give us this gives us 8.08. Right, so this is our mean of x. Okay, yeah, now that we have that, let's move on. We have here calculate x dash. Okay, yeah, calculate the test statistic. This is our final calculation. So yeah, let's do the calculation now. So before that, we have here 7 observations. Okay, so just something to note, we need to use the degrees of freedom here. So there are 7 observations, so we need to use 6 degrees of freedom, meaning that we are using t-distribution. So let's use t-distribution values. So our test statistic will be automatically t, and we plug in our value. So 8.08 minus that with 8.22, which is our stated mean as the question showed before, and we divide that with the root of S2 of x, which is 0.0453503, and we divide that with the number of terms it has, right? And that's what we had over here. Okay, and do note that this, we need to take the absolute value. Okay, we always take the absolute value. Whenever we calculate our critical value or test statistic, we take the positive value all the time. So let's put that in the calculator. 8 minus 8.22, divide that with root of 1351 divided by 30,000, and we times that by 7, and we get negative 1.745. but like I said, we take the positive value only, so 1.745. and as for our critical value, the next part over here, it says that we need to perform 1 minus alpha for a single tail test, and this is a single tail test. Yeah, this is a single tail test because we're only looking at values of mu that's lower than 8.22. So in a single tail test, we just use 1 minus alpha, where alpha is your significance level in decimal. Okay, so let's convert 10% to decimal at 0.1, and we just do 1 minus alpha, which is 0.9, right? So we have here 0.9 as our p-value, and our degree of freedom is 7 minus 1, so it's 6. So 0.9 we have to compare with 1.440, and so we just state our conclusions later with just a sec. Yeah, we do 1.745. 5 is greater than 1.440. So in this case, the test statistic is greater than the critical value, which obviously means that we must reject H null. Okay, so we reject H null. Reject H null. Okay, and then we state the hypothesis, and the hypothesis state that there is sufficient evidence to support the alternative hypothesis, or in other words like this: there is sufficient evidence to state that well, how would we do that? Mean is less than 8.22. Okay, in reality we just need to write this part, but it's difficult to write that on keyboard, and that's your answer right there. So that's for a single sample test, right? And now let's move on. We're getting a test the claim for a double sample test. Okay, so we have here a double sample test. Let's see which one has a double sample test. Now this is more of a difference test. I think the same one will have it, right? Yeah. Okay, now let's do a double sample test. Yeah, this is the one. So let's perform this calculation first. As for the confidence interval, we'll move on to this after this. Okay, so first let's read through the notes. So questions present data of two independent samples and ask whether the claim is justified to be true or not. All these data are given preset values or must be calculated. And yeah, this is just a past paper example where you have to use sum of x squared, sum of y squared. This is very important, as you need to know how to calculate these preset values here. Nx and ny always given to you. Sum x, sum y squared, sum y squared. Those are sometimes given to you. However, they can be calculated using a certain data values. So do note how to calculate these. So obviously you need to state the hypothesis if they've not stated in the question as shown before. Next we calculate S2 of x, S2 of y. Okay, so there are two samples, so we need to calculate two unbiased estimates. Now we need to calculate S2 or S2p. This is where people get confused because we don't know sometimes which one to use, pooled variances or do we use a normal unbiased estimate. So when do we use it? So it states that S2p, which is your pooled variance, is only used when the population variances are known to be equal. Okay, so they'll state explicitly in the question that the population variances are equal. Okay, only then do you use S2 of p. Otherwise we use S2 when the population variances are not stated to be equal. Next we need to do step 4, calculate sum x, mean x and mean y. So that's your calculation right here. Very easy calculation, can be done at any step except before the test statistic. Now there are two ways to calculate your test statistic and they diverge, they come directly from step 3. Okay, so if you've used the S2p value, we're going to use the second formula right here. If you're using the S2 value, we just use the first one. Okay, so yeah, something that you need to note. And finally, calculate critical value, get the critical value, compare, reject or accept. It's not very simple structure, very similar to our single sample test, except this time a new variables like S2 and S2p are involved and formulas have been slightly altered. Okay, in this case we just replace our mu with the y dash. Okay, so let's do a question to strengthen our basis on this. Okay, we've got ample space for this one. Yeah. Okay, so it states that the null hypothesis is mean A equals mean B and the alternative hypothesis. Okay, so one thing that you need to know right now is that it states mu A is not equals mu B, meaning that it's a two-tailed test because mu A can be greater than, lesser than mu B. Okay, so it's quite important that you know that this is a two-tailed test at 5% significance level. Okay, so I'm not going to state the hypothesis this time because I'm sure that you've got the concept already and that the question already states null hypothesis. So let's begin calculating the next step, which is S2 of x, S2 of y. So S2x, S2 of x equals to 1 divided by number of terms minus 1. Number of terms of, okay, so let's note down nx, which is equal to 50 leaves. So it's important that you take down these values. Next, without these values you cannot proceed to your S2 of x and S2 of y. 60. Okay, so we have all the values stated over here, and now that we have these we can proceed with our steps. So first calculate S2 of x, that is just 1 divided by nx minus 1, which is 49, times 1596 sum x squared. It uses the same formula as the single sample test, except we repeat it for the y samples. That's all that's been doing. And we divide that with 50. And this right here is your S2 of x value. Okay, so I'm going to plug that in right into the calculator. 1 by 49, 1596 minus 282 squared divided by 50. Which is the total number of samples from x. and this is our value for S2 of x. So I'm going to take the fractional value 138 by 1225. Very important that you have this value, and if you want you can write the decimal value, but do note that this value is what you really want. So 112, let's keep it 7. Yeah, okay. Next we have S2 of y. So S2y, and it uses the same logic as S2 of x. So over here we have 59. Oh, that's a bit absurd. Okay, yeah. So 59, because the reason I say 59 is because we just use ny minus 1 as stated here, and we just perform the calculation. So we have 1808 minus 328 the whole square divided by number of terms of y, which is 60, and this right here is your S2y, and let's just plug in these values. So 1 by 59 08 and this gives us, okay, another fractional value 224 by 885, and that's in decimal value will be 0.253 2531. Okay, that's your S2y. Now it doesn't state anywhere that the population variances are equal, right? Because the next step you need to calculate S2 or S2p. So we use S2 this time, and the reason for that is that it doesn't state anywhere that the population variances are equal. Okay, so we don't use S2p, we use S2, and I'll write that in different ink. S2 is equal to S2x. Okay, wait, I'll bring that back up. Yeah, so it's equal to S2x divided by number of terms of x plus S2y divided by number of terms of y. So I'm going to write S2 of x as the decimal value. So 1127 divided by number of terms of x, which is 50. We add that with 0.2531 divided by number of terms of y, which is 60, and we'll perform the calculation right now. So we have 138 by 1225, and we times that denominator by 50, and we add that with our next value, which is 224 by 885, times that by 60, and we get our S2 value as this. It's equals to 0.0064715, right? This is your S2 value, and yeah, that's your S2 value. Next we need to calculate mean x and mean y. So the next step, mean x, mean y. So what is mean x? That will just be let's just state that here. So we got, okay, so we need this exact value here. So what I'm going to use is I'm going to use this calculator here to calculate this. So 282 divided by number of terms of x, which is 50, which is 5.64, and the mean of y, which is y dash, equals to, that's the sum of y, 328, divided by number of terms of y, which is 60, which is 5.477 467. Okay, so which is just equal to 328 over 60. Fine, we can just plug this value directly into the calculator, no issues there. And now let's go to the concluding step to find the calculating test statistic. So we have to use this formula because we've used S2, not S2p. So mean x minus mean y, that's something that we need to use. So this time we use our z value, and the reason I say z value is because we have 60 and 50, and the total degrees of freedom over here is nx plus ny minus 2. So that is basically 110 minus 2, which is 108. And if you look here, we don't have any degree of freedom for 108, so we're going to resort directly to these values. So our critical value will be in terms of z. Right, so z equals to what? Let's see what z is equal to. Mean x, which is 5.64, minus mean y, which is 5.467. I'm going to use the fractional value, obviously, and we divide that with the root of s2, right? Yeah, 0.00647115. Okay, so this is our z value, and now we need to just put that in the calculator. So we have 5.64 minus 328/60. I'll just double check whether that's the mean or not. So yeah, that is. And we divide that with the root of the answer that we've calculated, and we get 2.154 equals to 2.154. Okay, that's your test statistic. Now we need to calculate the critical value. So over here it states this basically the same thing. For the level of significance, we divide the significance level by 2 for a two-tailed test. In this case we have to, and we perform 1 minus alpha. Okay, and for a single tail test we just do directly 1 minus alpha. This is just a repeated statement, but it still applies here. And for degrees of freedom, we've checked that nx plus ny minus 2 is not in the row of this t distribution, so it's present. So we're going to use this one. We use z values only, and using p get the appropriate value. So what is p going to be? So they're not going to mark you for calculating p, they're going to mark you for comparing your critical value. In fact, they don't mark you at all for even getting the critical value. So what is our p value? It says that it's a 5% significance level test. So we convert it to decimal as the document states. It says convert the significance level to decimal. We divide the significance level by 2. It's a double tail test, and the reason being said as mu a can be greater or lesser than mu b. So we have the single tail test, we divide by 2, and then we perform 1 minus alpha, which is this value here, 0.975, and also stated that the degrees of freedom do not appear in the t distribution, so we use this value, 1.960 p value. Okay, so we compare that with 1.960. So here we have 2.154, compare that with 1.960, and this is an obvious comparison. Our test statistic is greater than the critical value, and so we need to state that there is sufficient evidence to state that mean of a is not equal to mean of p. Okay, so we just need to write this part, but once again, keyword limitations. And yeah, that sums up your double sample test. Let's move on to confidence interval. Very simple question. For a single sample test, they usually give you 4 or 5 marks at the max for this. When they give 2 samples, they give higher than that. So let's see what they do. So the value is given, okay, and when I say given, they usually give. So this nx, which is the number of terms of x, is always given to you. Maybe they give you 7 data values and may not say that there are 7 observations, so you're gonna have to count them out. Either ways, this value will be accessible to you anyways. Sum x squared may need to be calculated. So yes, let's see what we have here. Step 1, calculate the mean. Okay, step 2 is calculating S2 of x. Step 3 is calculating critical value. So we have a little bit of the similarities with the test, except that we are just changing the steps. And finally, the most important formula for confidence interval is this one right here, where the only variation is that we use z or t. And like I've explained before, if you're using the critical, when you're calculating critical value, and nx minus 1, which is basically your degrees of freedom, does not appear in the t distribution, we use a z value. It's just that simple. Okay, just calculate critical value, do this, we get plus or minus, and we write in the form x comma y. Okay, and when we do the minus operation, so that means mean x minus this value, we get our x value, and when you do the plus operation, we get the y value. And then we write the answer x comma y, just like your coordinates, to get confidence interval. So it may sound a bit tedious and a bit too much intimidating in the first as I spoke, but this is not really very hard. So we only get 4 marks for this question, and Yes, S2 of x. Now we don't know how to calculate using the normal S2 of x. To calculate S2 of x, we need to use this formula right here, but we are not given that. We have this right here. So I've selected this question so that I show you how to use this value to get S2 of x. So they've given us our mean, so that's our first step already is skipped. Mean doesn't need to be calculated. S2 of x, however, is a bit more complex because of no sum x squared. But this is now easier actually, because now we just need to plug in a simple formula. So yeah, we just use this minus x mean whole squared, which is just the value right here, and we divide that with the number of terms of x minus 1. Okay, so using this formula right here, we can calculate. So 78.5, divide that by number of terms of x, which is 10 students, minus 1, so 9, and we have here 157 over 18. 157 over 18, and that is just 8.72 recurring. Okay, so that's your S2 of x. Next step, calculate critical value. So we have 10 samples here, 10 samples, so degree of freedom will be 9, which is just 10 minus 1, and we do know that 9 appears in the t-distribution table, meaning that we use this formula here. Okay, so we use this formula, and yeah, just state that. So we have our t value, sorry, we have our nu, which is our degrees of freedom, so we know that a critical value will lie anywhere here. And the next step is obviously to calculate the p value. How do you calculate a p value for confidence interval? This time you don't need to look whether if it's single tail or double tail. It's always this formula right here. So over here we use this confidence interval specified in the question, alpha plus 100 minus alpha divided by 2. So in this case our alpha is 90%, so it's basically going to be 0.9. We need to convert it first, then we divide plus that with 100 minus 9. Okay, let's not convert it. Okay, so this formula that I've stated is working in terms of percentages. Okay, so 100 minus 90 divided by 2, and that is equal to 95%. So that's basically 0.95. So what I've done basically over here, instead of using the formula and not understanding the logic, I'll explain to you exactly why I use that formula. So we are basically just trying to find the midpoint between 90% and 100%. So if this is 90% and this is 100%, we need to find the midpoint right here. Okay, so our midpoint will be somewhere here, let's say, and we don't know that midpoint, so we just need to calculate, and we can easily say that it's 0.95. However, if you do struggle with it, you just use the formula over here and you should be good. Yeah, so we found our p value to be 0.95, so let's put that over here, and we have 1.833. This is our critical value. So now that we have all the values needed for this calculation here, let's just plug it in. So confidence interval, yeah, so CI, which represents confidence interval, is your mean of x, which is 25.6, plus or minus, very important you put plus or minus, 1.833. we root that with S2 of x divided by number of terms of x. So basically 8.72 divided by number of terms of x, which is 10. Okay, so just perform this calculation, and what I'd like to do to solve these kind of questions, I'm going to show you right now. So here we have 1.833. okay, so I'm going to just calculate this value right here, just this value here. This is what I do. So 1.833 root, and then we get 8.72, we write in fractions, 157 divided by 18, and we times the denominator by the number of terms, 10. And this is what I do right now. So 25.6 plus or minus 1.712. Writing this down keeps confidence intervals much easier to do. And now we have our confidence interval. We can go directly to the answer. So what I've stated over here, it says that the negative operation makes up the x value, and the positive makes up the y value. It's just a simple understanding way. And so we can use 25.6 minus this value, and that's your first one, so 23.9. okay, and then we comma that with your other value, which is your y value. How do we get our this value here? You could calculate it again, or just use 25.6 minus your x value to get the value back, and then we add that with 25.6, which is your y value. So you get 27.3, and that's our confidence interval. Worth 4 marks. I completely agree with the marking, of course, because they've given us most of our points needed. Right. Moving on, we have double sample confidence interval. So let's just cut this and this off. Yeah. So let's solve the double sample confidence interval. Okay, fine. So first step is to calculate mean x, mean y, just as the previous one. Second step is to calculate S2 or S2P. Do note that I have not said to calculate S2x and S2y because it's going to be too much repetition. I'm pretty sure by now, this much into the document, you know how to calculate S2x and S2y. Third step is to calculate your critical value. So we know how to do that. P value and degrees of freedom. Whenever there are two samples, we use this nx plus ny minus 2. And usually for double sample test, it's usually not present, and we use the z values. Okay, so we don't usually use t values for double sample test. And finally, we apply the formula to get this. Okay, so we use the modulus of the two means, the difference between the two means, and we modulus that, only the positive value. And then we do plus or minus z or t, which is just right here, but I need to write 4 formulas if that's the case. So I just put z or t times that with root s2 if you're getting s2. And if you're using s2p, well, use this. But so far, they're not going to be asking you this. Usually, they do not ask this. But in case they do, just remember to use that. Well, yeah, that pretty much sums up your confidence interval value. Use x comma y, and yes, it's pretty much like the single sample test, except we use pooled or normal combined variance. So let's solve this one. We need to first calculate your mean x. So mean x equals to 89 divided by number of terms of x. Oh, right, we need to state number of terms of x first. So number of terms of x, 50 adult males. So 50 adult males and 40 adult males of country B. So ny equals to 40. Okay, so 89 divided by number of terms of x, which is 50, 1.78. 1.78. And as for number of mean y is equal to number of terms of y, so 67.2. divide that with number of terms of y, which is 40, and you get 1.68. That's your value for mean y. So we've done the first step. The second step to calculate S2 or S2P. Confidence intervals normally give you only S2, but first of all, we need to calculate S2 of x, and that can be just solved directly. So 1 divided by number of terms of x minus 1, so 1 by 49 minus, sorry, not minus, bracket 159.4 minus that with 89 squared, divide that with number of terms of x. So we have this is your x value. So let's solve that right now. So 1 by 49 bracket 159.4 minus that with 89 squared, divide that with 50, and there you have it. We get 1 by 50, a nice value, 0.02. Yeah, we have a nice value there. As for y though, I don't think it's going to be a very nice value, but we'll see. So S2y now. That, okay, let's zoom that in a bit. So S2 of y, we have number of terms of y, so it's 40 minus 1, which is 39. And we bracket that with sum y squared, which is 113.1. Minus that with sum y the whole squared, 67.2 the squared divided by 40, right? And this is your S2 of y. So let's calculate that as well. So 1 by 39, 113.1 minus that with 67.2 squared divided by 40, and this is your S2 of y. Okay, fine. So we have 173250, and that's same as your decimal value, which is 0.050523. Let's just put 523. Okay, now do we calculate S2 or S2P? Nowhere does it mention that the population variances are equal, so we don't use S2 of P, we use just the S2 formula, which is a rather more simpler formula as I'd stated. So yeah, let's do the S2 formula. S2 is equal to 0.02 divided by number of terms of x, which is 50, and we add that with S2 of y divided by number of terms of y, 523 divided by 40 terms. And let's perform this calculation right here. 0.02, which is S2 of x, divided by 50 times your answer. I saved our S2y as answer, and we divide that with number of terms of y, which is 40, and we get this fractional value here, 1300. But do note that they don't give you marks for the fractional value a lot, so you're gonna have to write the decimal value more frequently. 531. Okay, so they usually mark you for the decimal value, and yeah, but you should use the fractional value all the time. And yeah, now that we have our S2 value, we can proceed with the calculations. Before that, calculate the critical value. So as I've stated before, in the double sample test, they usually give huge number of samples that they don't appear over here. Frequently they don't, but there are times where they do, so take caution in that. But in this case, we're going to use our Z values. Right, so for the Z values, we need to calculate the P. So as I've stated, for the confidence interval, we just need to find the midpoint between our confidence interval 95% to 100%. So the midpoint between that is 97.5%. That's your P value. And yeah, you could use the formula right here if you don't know how to calculate, but it's really very mental just to calculate that. So 0.975, 1.960 corresponds to that. So now let's calculate the confidence interval. So CI is equal to mean x minus mean y, the modulus of that. So 1.78 minus that with 1.68. Okay, we take the modulus plus or minus. Now we use a Z or T value, but since we're using the critical value from the normal distribution here, we use 1.960. 1.960 times the root of S2. Right, we use the root of S2 here, and our S2 value is this value that we've calculated here, 0.000531. right, that's your S2 value. So yeah, let's just perform the calculation. As I stated before, I first calculate this and I'll calculate this later. So we can directly calculate the mean x minus mean y, which is 0.1 plus or minus. Okay, so yeah, we do. Okay, so our answer was this. So yeah, we do 1.96 times root of answer. So we have here 0.04552, and now our confidence interval is going to be, well, I told you the minus operation dictates your x value and your plus operation gets you your y value. So let's perform the x value first. So your confidence interval equals to, let's do 0.1 minus answer, which is 0.0458 0548, comma that with your answer was this, and then you minus that with, now we add 0.1 to it and we get 0.145. So that right there is your y value for the confidence interval. And yeah, that pretty much sums up all of that is for double sample confidence intervals. And I hope you enjoyed this video and understand now how to do the inferential statistics based questions. Yeah, so that pretty much sums up this. Using this itself can get you a free 15 marks. Just remember the formulas and yeah, you should be good. So thank you for watching and see you until next time.